G'day guys, today we've got an optimization question for you. Specifically, we're optimizing the volume of a cardboard box with an open top. This question, I would say, comes up more often than not in exams and tests in like high school calculus. So I'd learn how to do this specific question just in case if it comes up in your test/exam. So let's get to it. We've got a square sheet of cardboard with each side A centimetres is to be used to make an open top box by cutting a small square of cardboard from each of the corners and bending up the sides. What is the length of the small squares if the box is to have as large a volume as possible? Okay, so that last little bit there, large as volume as possible. So I usually write a little note to myself of what I'm trying to do. So I'm trying to maximize the volume of the box. Cool. So what we should do as well, after we've read this question, it's probably a good idea to draw a picture of the situation we're given, like the one I prepared earlier. So here we've got our cardboard box would be the sort of the aqua line plus the dashed line, which we've marked X, would be our original cardboard box. And we've cut out these edge pieces marked X. So what we're going to have left after we've cut out these pieces marked X is we're going to have a base which takes this area here, and these edges will fold up to make the sides of the box. So to work out the volume, we're going to have the area of the base times the height. So the volume of this box is going to be the area of the base times the height. And the area of the base is going to be a minus 2x on both sides. So it's going to be a subtract 2x all squared. And the height of this box is going to be times x. Cool. So we can rewrite that by expanding out our brackets, and we get the volume is going to be equal to a squared x minus 4ax squared plus 4x cubed. Cool. So that's our equation for the volume of this box in terms of x, because a is going to be a constant. We're not using any side length here. We've just got a coefficient as our side length. So we're going to be working out x as a proportion of the side length a. Cool. Well, let's go about doing that. So to be able to optimize this, what we're going to have to do is we're going to have to differentiate volume in terms of x. So we're going to calculate the dv dx, which is equal to a squared minus 8ax plus 12x squared. And the optimal value of our volume will occur when this is equal to 0. Now, a lot of you from here would go to your sort of graphics calculators and ask that to solve it for x. The reason that this is in terms of a is to stop you from doing that. So what we're going to do now is we're going to factorize this expression, and then we're going to use the Null Factor Law to solve it. So to factorize this quadratic, we're going to go a minus 2x, a minus 6x equals 0. And from there, what we can do is the null factor law says if we have two numbers that multiply together to give 0, either this has to be equal to 0 or this has to be equal to 0. So let's start with a minus 2x equals 0. So a would have to be equal to 2x, and therefore x is going to have to equal a divided by 2. So there's one of our critical points, and let's go to the other one. So we have a take 6x is equal to 0. So therefore a is going to have to equal 6x, and x will equal a over 6. Now, we've got two critical points. Now what we have to do now is we have to use our own common sense to figure out which one of these points is going to be the one that maximizes the volume of this box. Now, this first one here, x is equal to a over 2. So if x was equal to a over 2, it would mean that the cuts in our corners would come all the way to here. So you wouldn't have a base of the box. The whole box would be cut away and the volume would be equal to 0. So let's write up here a little note to ourselves. So we've got at x equals a over 2, if we cut out half of the side lengths for each of the heights, the area of the base is going to equal 0. So as a result, the volume will equal 0. So as a result, the only other critical point we have is a over 6. So that must be our maximum. So we can say, therefore, max volume occurs when x is equal to a on 6. Okay, so let's have a look at what we did to solve this question. So first of all, what we did is we read the question carefully and we found out what it's asking us to optimize. And to be honest, I write a letter to myself or a note to myself, but I'm also writing a note to the examiner explaining that I know what the question is asking me to do. After I've done that, I derive an equation based on the information given in the question, and I came out with this. Now, I'm getting ahead of myself here. What I did before I came up with this is I drew a sort of a basic representation of the problem. So once I've drawn my picture, I'm also displaying to myself and the examiner that I kind of know what the question is asking me to do. So even if you get muddled up in the algebra and the differentiation, you're telling the teacher that you know what the hell is going on. You know what it's asking, you can read, and you might be able to snag a few marks in there somewhere. Once I then come up with an equation for volume, or what the objective function is that I'm supposed to optimize, I then differentiated it and set it equal to 0 because I know that my critical points are going to occur when the derivative of this function is equal to 0. I then factorized my derivative so I could exploit the Null Factor Law to try and find when x was equal to what x was equal to when the function equals 0. I came out with two solutions, as you'd expect from most quadratic equations. I then used my common sense to find out that one of the solutions was going to give us a volume of 0, so would be discounted. And the other solution was obviously going to be, by process of elimination, this was going to be a maximum. So after I did that, I then, wrote down a statement displaying my answer to the examiner, and then I moved straight on to the next question. So guys, I hope the video helped. If it did, definitely give it a thumbs up. If you'd like, subscribe to my channel. I put out new videos all the time on maths, physics, chemistry, you name it. I'm always looking for new topics to put my videos on. So if you have any problems with your schoolwork, don't hesitate just to leave them in the comments section below, and I'll try and get to them as soon as I possibly can. Until next time, guys, I guess enjoy your maths.